Hello, welcome back to Educator. Today we're going to be talking about carboxylic acids. Let's review what we know about carbonyls that we've seen in aldehydes and ketones so far. A carbonyl is a CO double bond, and what makes this functional group very special is that it has resonance, where we could draw a second Lewis structure. And anytime we have resonance, that means that neither of these Lewis structures accurately reflect the actual structure of the carbonyl. It's some blend between these two. And so, but each of them kind of describe the characteristics that the carbonyl have. So overall, every time we see a carbonyl, we know that the carbonyl carbon has some significant partial positive character and the carbonyl oxygen some partial minus character. And that means, the reactions we've seen so far is that the carbonyl carbon is electrophilic. In other words, nucleophiles adhere. And the carbonyl oxygen is somewhat basic. In other words, we can protonate here. And in fact, many reactions we've seen have started with, involve protonation of the carbonyl, and many reactions involve nucleophilic attack on the carbonyl carbon. So let's just review a few examples of these we've seen already for aldehydes and ketones, because then we'll be able to compare that to how that differentiates or is different from when we move into carboxylic acids and other functional groups known as carboxylic acid derivatives. So for example, if we have a ketone and we treat it with hydride, something like lithium aluminum hydride, that is a great nucleophile. We would expect that to add to the carbonyl, and then after workup, we would protonate that O-, and we would get this alcohol product out. So we describe that as a reduction reaction because we have lost a CO bond, traded it for a CH bond. We've gone from a ketone to an alcohol. Okay, a Grignard reaction gives, instead of an H-, it gives us a C-. So this phenylmagnesium bromide would give us a source of phenyl-. We could put that in quotes just like we did for hydride. Sorry, I didn't do that. We should put that in quotes because this hydride is always coordinated with the aluminum. This carbon group is always coordinated with the magnesium, but it reacts just like that kind of nucleophile and again would attack the carbonyl, and then after an aqueous workup we would end up with an alcohol product, but in this case we would have a new carbon-carbon bond that we've also formed at the same time. So this is just a few examples of nucleophiles that can add to carbonyls of aldehydes and ketones. Now, if we have heteroatom nucleophiles like oxygen or nitrogen, our products look a little different. If our nucleophile is an alcohol, you can imagine that the same pattern we had for the hydride or the Grignard, our nucleophile in this case would be a methoxy group, so we could add that in. But this alcohol product is no longer stable. Having a single a carbon with an OH and an OR group attached is not stable. So instead, this continues to react in the presence of acid catalyst, and we end up adding two equivalents of the alkoxy group, and we get out a product known as an acetal. So instead of having a carbonyl, two bonds to the same oxygen, we have two bonds to different oxygens. We have these methoxy groups. And if we have a nitrogen nucleophile, again, you can imagine having this as an intermediate product, okay, but this too is unstable, having this alcohol, because this nitrogen with its lone pairs is going to come down and kick off that leaving group at some point. We would probably protonate this since we're acid catalyzed to make it a good leaving group. But ultimately, the product we get with an aldehyde or a ketone and an amine is we replace the CO double bond with a CN double bond to give an imine product. So these are all reactions we've seen before for aldehydes and ketones, and we'll see how those are going to be quite different from the next set of carbonyl-containing functional groups. We'll see carboxylic acids and their derivatives. Now, a carboxylic acid is the functional group we have, and we have a carbonyl, but instead of just carbons attached like a ketone or a carbon and a hydrogen like an aldehyde, we have an OH group attached to that carbonyl. Now, that no longer is an alcohol functional group or a ketone or an aldehyde. This entire thing combines together to be described as a single functional group called a carboxylic acid. And if we want to think about its reactivity, we need to consider its resonance as well. And like every carbonyl, it has resonance that breaks the pi bond and gives an O- and a C+. Right? That's always true for any carbonyl. But by having this OH group now attached to the carbonyl carbon, we have additional resonance. And that additional resonance comes about by this oxygen donating its lone pair of electrons and sharing it with that carbonyl, carbon. And we have a third resonance form that we can draw. So how does that affect the reactivity of the carboxylic acid? Well, it turns out that this oxygen group with its lone pair donates electron density into the carbonyl. The OH group donates electron density. And that means that this carbonyl of the carboxylic acid is more electron rich than a ketone or an aldehyde. The effect of that oxygen is to add electron density to the carbonyl, making it more electron rich. That makes the ketone or the aldehyde more partial positive and more electrophilic. So carboxylic acids and their derivatives, we'll see down the road, in general are more electron rich because of that electron donation, certainly if you have an oxygen group here like an OH. And an example that we've seen of this before is when we use sodium borohydride as our hydride source instead of lithium aluminum hydride. LAH is much more reactive. Sodium borohydride is not as reactive. It's still reactive enough to react with a ketone and reduce it to the alcohol. Okay, but if we try to do that same reaction with an ester, the ester, remember, is less reactive because this carbonyl is more electron rich. We find that there's no reaction here. So sodium borohydride is, we say that NaBH4 is selective for aldehydes and ketones. It can reduce an aldehyde or ketone in the presence of an ester because the ester is less reactive. Now, in this lesson, we're going to be talking about carboxylic acids, but the next lesson, we're going to be talking about all the related functional groups called carboxylic acid derivatives, and let's introduce them at this point. If you have a halogen attached to a carbonyl, we call those acid halides, and usually the X is chlorine, so it's usually the acid chloride that we're dealing with. If you have an oxygen surrounded by carbonyls on either side, that's known as an anhydride. If you have an OR group attached to the carbonyl, it's called an ester. And if you have a nitrogen attached to the carbonyl, we call that an amide. So these all have the general structure of having attached to the carbonyl some kind of leaving group with a lone pair. So this represents an atom with lone pairs. We describe it as a heteroatom, meaning not carbon or hydrogen. If it was carbon or hydrogen, we describe it as an aldehyde or a ketone. But this has what? It has either a halide. We know halides, of course, are good leaving groups and have lone pairs. The leaving group on an anhydride is this oxygen with the carbonyl. So for an anhydride, one of the carbonyls we consider as the electrophilic carbonyl. The rest of the group, the other carbonyl, is part of the leaving group attached to that. The ester has an OR group attached as a leaving group. The amide has a nitrogen group attached as a leaving group. And then the nitrile doesn't really fit into the same pattern, but it too is a carboxylic acid derivative because it has 3 bonds to a nitrogen, for example, instead of 2 to an oxygen, 1 to a nitrogen. Still has that same sort of pattern. We'll look at nitriles a little later in the chapter. And the reason that all these functional groups are grouped together and considered as a unit is because they have the same general reactivity, okay? And a general reaction of a carbonyl with a leaving group attached is that when it reacts with the nucleophile attacks the carbonyl, and then it might be tempting, now that you see something defined as a leaving group attached, it might be tempting to say, oh, well, that nucleophile just kicks out that leaving group, doesn't it? Well, it can't. That would be an SN2 mechanism. There's no SN2s for carbonyls. Carbonyls don't do that. But instead, the nucleophile attacks the carbonyl and, as always, just breaks the pi bond and puts those electrons up on the oxygen. Okay, but when you look at the structure that's formed as a result, this structure is described as a charged tetrahedral intermediate. Charged tetrahedral intermediate, or a CTI for short. And what defines a CTI is you have a tetrahedral carbon, so in other words, an sp3 hybridized carbon with 4 groups attached. And we have an sp3 hybridized carbon, and at least 2 groups have lone pairs, have 1 or more lone pairs. So, for example, if we have an oxygen and an oxygen, or an oxygen and a chlorine, or a chlorine and a nitrogen, if we have 2 groups, at least 2 groups with lone pairs, we describe this as a CTI. And what a CTI does is very special. It will collapse. When we see this pattern in an intermediate, we know that it is unstable, and it collapses. And what that means is that the leaving group will leave, but it leaves with the assistance of the other group with lone pairs. So one group with lone pair gets kicked out, and the other group with lone pairs helps push it out. And so our leaving group leaves, and overall what's happened is we've had a substitution reaction take place. Our leaving group is gone, and a nucleophile has taken its place. Okay, but it's not a substitution mechanism we've seen before for alkyl halides, for example. It's not an SN1 mechanism. It's not an SN2 mechanism. It's called an acyl substitution reaction. The mechanism can be described as addition, elimination. Our nucleophile adds into the carbonyl, and then the leaving group is eliminated by collapsing a CTI. We'll find that it has both acid-catalyzed mechanisms and base-catalyzed mechanisms. We'll study both of those in today's lesson. Before we look at those reactions, though, let's think a little bit more about carboxylic acids as a functional group. What kind of behavior does it have? What kind of physical properties? Okay, so for example, let's take a look at this guy. This is acetic acid. This is a simple carboxylic acid. ACOH is how we could abbreviate this. The AC group means we have a CH3 with a carbonyl. You'll see that AC group here in acetic acid, and it's common throughout all the carboxylic acid derivatives, acetyl chloride and acetic anhydride and acetamide and so on. So it's very good to be familiar with those common names. So if you take a look at the physical properties, acetic acid is an interesting one because this is the acid, the acidic component that's in vinegar. So the odor of acetic acid is very familiar to you. The bite that it has, the flavor that you have, that kind of burning sensation is this component in here. And what does it have on here? Well, all carboxylic acids have the OH group. We know that the OH group is very polar. And it's very polar. It can, anytime you have an OH bond that's so polar that those groups can interact with other OH groups and can form hydrogen bonds. It's polar. It can form hydrogen bonds. It can form hydrogen bonds with itself. So 2 molecules of acetic acid, in other words, can hydrogen bond to each other. That means it's going to have a high boiling point. And it can also form hydrogen bonds with water. That means it's going to have high water solubility. And in fact, that's true. The boiling point for vinegar is 118 degrees Celsius. So even higher boiling in water, very high boiling compound, and it's miscible with water. So that means it's very highly water soluble, and in fact, vinegar is an aqueous solution with acetic acid in there, dilute aqueous solution. And so you can't ever add enough acetic acid to water to have them separate out into 2 layers. It's always going to be a single solution because it's miscible. It's soluble in all proportions. Okay, and that's because it has this OH group. In addition, it also has this second oxygen, has the carbonyl, which of course is also polar and can do the same thing. It can hydrogen bond, it can form hydrogen bonds with water. In other words, it can be a hydrogen bond acceptor. So there's a lot of characteristics of a carboxylic acid that make it very familiar with water and very, very much like water. Okay, so when you see the RCO2H, that's how we abbreviate the carboxylic acid. When you see that functional group, it is an extremely polar functional group. And remember, it has that resonance that we looked at on the first slide too, on an earlier slide, that makes it even more polar with partial positives, partial negatives. Okay, so it's an extremely polar functional group. Now let's take a look at a different carboxylic acid. This one has now a longer carbon chain. So it has two parts of the molecule. It has this carboxylic acid part, which is quite polar, can hydrogen bond donate, can hydrogen bond accept. So this part we would describe as being quite hydrophilic. But how about the rest of this carbon chain? Carbon-carbon bonds, carbon-hydrogen bonds are totally nonpolar. So that makes them nonpolar. That makes them hydrophobic. Or you can even describe it as being greasy. This is something that would not like water at all. So this actually has a pretty low solubility. This is insoluble in neutral water, this molecule. But if we, instead of using neutral water, if we were to use sodium hydroxide in water, basic water, what would happen is the base would react with the carboxylic acid functional group. And we'll look at this reaction next. And that would make an ionic compound. Now that goes from being, just a very, very polar functional group to an ionic functional group. That's as extreme in polarity as you can get when you have full charges. Okay, so that makes it more soluble in water. Ionic compounds love water. And so what happens is we can use base as a way to increase the solubility of a carboxylic acid by this chemical reaction that it undergoes. The product of that acid-base reaction is an ionic and therefore more water-soluble carboxylate salt. So let's talk about the acidity of the carboxylic acid. It must be a significant physical property if that's actually part of the functional group's name. If we go back to looking at an alcohol, an OH group that's just on an ordinary carbon chain, that has a pK somewhere around 18. And a carboxylic acid where that OH is attached to a carbonyl has a pK somewhere around 5. So that is 13 pKa units, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, I don't even know what that number is. So gajillions times more acidic by being a carboxylic acid OH instead of an alcohol OH. And so we'll talk about why that is in just a second, but right away let's think about the choice of base. If you wanted to deprotonate an alcohol, it's not a very easy thing to do. You have to use an extremely strong base. We use something like sodium hydride. Okay, a stronger base is needed. And furthermore, this is a base that is irreversible, because once you deprotonate, you would have the sodium salt here. And what's the other product you form? If you're using H- as your base, it abstracts an H+, you end up with hydrogen gas. Okay, so that was a way that we could make alkoxides. If we wanted to make an alkoxide, we would take an alcohol, we'd treat it with sodium hydride. Very strong, irreversible acid-base reaction. Let's compare that to a carboxylic acid. Most definitely, sodium hydride would effectively deprotonate a carboxylic acid, but we don't need a base that strong. We could use something like sodium hydroxide, and here a weaker base is okay. And of course, we typically want to use the weakest base possible because that's going to be cheaper, it's going to be easier to handle, and so on. Okay, but that will give us the sodium salt. Again, we get an O minus, sodium plus. This is called a carboxylate salt when you've got an O minus attached to a carbonyl. And our other product here, when we use hydroxide, is water. That has a pK on the order of 16, and so that wouldn't be strong enough to totally deprotonate an alcohol, but again, very, very easily deprotonates a carboxylic acid. This reverse reaction is essentially non-existent when there's such a big difference in the pKa's, 16 compared to 5. Okay, so one thing for this to keep in mind is that anytime you have a carboxylic acid exposed to basic conditions, things like hydroxide, alkoxide, something like that, you no longer have a carboxylic acid. You now have a carboxylate. We always need to keep that in mind. We can actually use that, like we just saw on the previous slide, for extraction purposes. That would be very handy. But we'll also see some cases where we have to keep that in mind when we're doing our reaction mechanisms. Okay, let's talk a little bit, since acidity is such a big component of a carboxylic acid's identity, let's talk a little bit more about these pKa's. Why do we have this huge difference here? How can we explain that? Let's make sure we're clear on that. And as usual, the way we're going to determine the difference or explain that difference is by looking at the conjugate bases. So let's look at alkoxide versus a carboxylate and see why it's so different getting from one to one versus the other. Okay, if we have a carboxylate and an alkoxide, they both have a negative charge on oxygen, so they're both reasonable anions to have. Oxygen doesn't mind have a negative charge, but one is so very different from the other in terms of stability, and that's because this O minus is attached to a carbonyl. That makes it allylic, and that makes it available for resonance. So anytime you have resonance delocalization, that's a good thing. Anytime you can delocalize the negative charge over two oxygens, that's a good thing. In fact, these two resonance forms are equivalent to each other. That's the best possible resonance stabilization you can have, because each of them is contributing 50-50 they're contributing equally to the overall hybrid. So that's fantastic resonance stabilization. Okay, so this has a resonance stabilized. This is a resonance stabilized conjugate base. We're really delocalizing the negative charge. That's a great thing. Anytime you can spread a negative charge out over multiple atoms, that's an excellent thing. So that makes him less reactive. If you are more stable, that makes you less reactive. That makes him the weaker conjugate base. This is the less reactive, weaker conjugate base. And the weaker conjugate base is the one that has the stronger parent acid. It has the stronger parent acid. And is that what the pKa data told us? Yeah, this was the pKa that was somewhere around 5. Real low number. Very, very good acid. Okay, we compare that to the alkoxide. Now again, oxygen doesn't mind have a negative charge, but it's all relative. We're just comparing this to a different O minus. This one is resonance stabilized, this one is not. So this has no resonance. So there's nothing additional to stabilize that negative charge. There's no way it can be delocalized over different atoms. Okay, so if he is less stable, higher energy, that makes him more reactive. This is the more reactive and therefore stronger conjugate base. The stronger conjugate base has the weaker parent acid. Has the weaker parent acid. And again, going back to that pKa, this is the pKa that was somewhere around 18. Okay, so most definitely you should have a good understanding of why it is carboxylic acids are such effective acids and what makes the carboxylate conjugate base such a stable species. Okay, the take-home message that we've seen before and we're seeing again is that if you have something that will stabilize the conjugate base, then that makes the acid a stronger parent acid. That's always what we're looking for, is something to stabilize the conjugate base. Let's take a look at another example. Let's compare acetic acid to trifluoroacetic acid. And the question is, which is the stronger acid? Well, I don't see a difference in these two acids. They're both neutral. They're both stable. There's nothing unreasonable there. But what we need to do is we need to look at the conjugate bases, because those are charged species, and see if we can find a difference in their stability there. So in other words, let's let each of these acids be an acid. Let's deprotonate them. And of course, we're talking about the proton that's on the oxygen. That's always going to be the most acidic proton in a structure. So where we used to have an OH, now we have an O minus. And same thing over here, where we used to have an OH, we have an O minus. Okay, now in this case, we're looking at they're both carboxylates, right? So they both have the same resonance. So we need to find some other difference. The difference, of course, is that here we have hydrogens on the CH3. Here we have fluorines. Okay, and what effect is that having? Well, what do you know about fluorine? We know that fluorine pulls electron density toward itself. Fluorine is electronegative. That means it pulls electron density toward itself. So let's start by stating some facts here. We could say fluorine is more electronegative than hydrogen. Right? So then we can say that fluorine withdraws electron density. Withdraws electron density inductively. This is an inductive effect, meaning there's not a resonance form we could draw for this. We just use this arrow showing that the electrons in these bonds are being pulled toward the fluorine. They're being pulled toward the fluorine, and therefore this carbon-carbon bond is being pulled as well. Okay, so those are the facts. Here's the tricky part. Is that a good thing, or is that a bad thing? Is that something that helps to stabilize this negative charge, or is this something that causes the negative charge to be destabilized? That's the tricky part. Okay, and let's think about what that negative charge means. A negative charge indicates to us that there is an excess of electron density. There's too many electrons around that oxygen. And what are those fluorines doing? They're pulling some of that electron density away. Kind of sounds like a good thing, doesn't it? Yes, it's delocalizing. It's helped moving and spreading it out through the molecule. Okay, so this stabilizes. This stabilizes the negative charge. That's a good thing. It delocalizes it. Right? It puts some of the negative charge out on these fluorines. Okay, so that means let's call this guy A and B. So this is conjugate base A and conjugate base B. That's always a good idea so that we can refer to things by name. So what we can say here is that conjugate base B is the more stable and therefore less reactive and therefore weaker conjugate base. It's more stable, therefore less reactive, and it's the weaker conjugate base. So conjugate base B has the stronger parent acid. Has the stronger parent acid. And that was our original question, right? Which is the stronger acid? That was B. So B is the stronger acid. Okay, something that stabilizes the conjugate base makes for a stronger acid. If we take a quick look at an energy diagram and we compare the energies of A and B, are relatively similar in energy. There's no big difference between A and B. But then when we look at their conjugate bases, we see that A, conjugate base A, is higher in energy than conjugate base B. The presence of those fluorines helps to stabilize, lower the energy of that conjugate base. So B being deprotonated is an easier path than A being deprotonated. This is more favorable. So something that stabilizes the conjugate base makes it the parent a stronger acid. So we saw how resonance can do that, and here's an example how inductive effects can do that. So trifluoroacetic acid is a stronger acid than just ordinary acetic acid. Now, one more thing about inductive effects is that they decrease with distance because they are a through bond effect. The more bonds it has to travel through, the less and less effect you see. So, for example, if you had a fluorine 10 carbons out from your carboxylic acid, the carboxylic acid wouldn't even know that the fluorine's there, and it would have no effect on the pKa, for example. So here's an example of some compounds that you can see that. Here we have carboxylic acid attached to benzene. This is known as benzoic acid. It's good to know some of these common names for, or this is the IUPAC name for a common name for this carboxylic acid. We'll see it a lot. And here we have some substituted carboxylic acids. Here we have the fluorine in the para position. This is called para-fluorobenzoic acid. This is in the meta position. This is in the ortho position. Okay, the benzoic acid itself has a pKa of 4.2. So what do you expect for these fluoro-substituted benzoic acids? What do you think is going to happen to the pKa? We would expect these fluoro-substitute ones to be more acidic. What does that do to the pKa? It lowers the pKa. So we expect them all to be lower than 4.2, and they are. But the one where this fluorine is really far away, very, very slightly lower. It's 4.1, just barely any difference at all. And when it's meta, it's 3.9. And when it's ortho, it's 3.3. So almost 10 times more acidic by having the fluorine here. And this is quite far away from the O-. So it tells you that these inductive effects can be pretty powerful. They all have the same resonance. The carboxylate conjugate bases all have the same resonance, but it's these inductive effects that are affecting their pKa's. So let's talk about the preparation of carboxylic acids. Where do they come from? How can we get a carboxylic acid product? Well, because the carboxylic acid carbon is highly oxidized, it's got 3 carbon-oxygen bonds, one way we can get there is by doing an oxidation reaction. We could start either with a primary alcohol or an aldehyde. Both of these carbons already have a CO bond, and they also have hydrogens that are capable of being lost to oxidation. So if we treat this with a very, very strong oxidizing agent, then we would expect that carbon to be fully oxidized to the carboxylic acid. Right? These are both 2-carbon substrates, so we would get acetic acid as our product here. What are examples of strong oxidizing agents? Things like our Jones oxidation chromic acid, so sodium dichromate and H2SO4, KMNO4 permanganate, and base is very good. Okay, but notice because we have base here, what's going to happen to the carboxylic acid product as it's formed? It will be deprotonated, and so if you want the neutral product when you're all done, you have to do an H3O plus workup. Okay, that's just a little note down here. Basic reactions require an acidic workup if you want to get the neutral carboxylic acid product out. Okay, same thing for this oxidizing agent. This is known as Tollens reagent when you use silver oxide. It also requires base, so we have to do an H3O plus workup in this case. This is an interesting reaction because we use silver plus to carry out the oxidation, and of course the oxidizing agent itself gets reduced when it takes the electrons, and so it goes from silver plus to silver zero. Well, silver zero is silver metal, and so the Tollens test is a test for aldehydes. If you treat it with silver oxide, it'll form silver metal, and the silver metal, if it's done just right, can plate itself out on the inside of the glass wall of the test tube, and you can get a mirror that's formed in this reaction. So this is known as the silver mirror test for aldehydes, for RCHO, and the reaction involves oxidizing the aldehyde to a carboxylic acid. Of course, these qualitative tests are not nearly as widely used anymore because we have spectroscopic techniques that can do a better job of quickly and easily analyzing our function groups that are present. So we can oxidize primary alcohols or aldehydes to get a carboxylic acid. We can also oxidize an alkene or an alkyne by doing an ozonolysis reaction. So reaction of an alkyne with ozone totally breaks the carbon-carbon triple bond. All 3 carbon-carbon bonds go to carbon-oxygen bonds, so the product you get out is a carboxylic acid. We would get benzoic acid and acetic acid in this case. So ozonolysis of an alkyne does that. Now if we do ozonolysis of an alkene, if we do it with just an ordinary reductive workup, we would get out 2 aldehydes in this case. See how this double bond has a hydrogen at each position? So we would get benzaldehyde and acetaldehyde in this case. But we just learned that if you had an aldehyde, you could take these and you can oxidize them up to the carboxylic acid. So you could use Jones oxidation or something like that, and you could get the carboxylic acid instead. Okay? Or we could go straight from here to the carboxylic acids by doing ozonolysis, and instead of doing a reductive workup where that you keep these hydrogens, you can do what's known as an oxidative workup, where instead of treating it with a reducing agent, you treat it with an oxidizing agent like hydrogen peroxide, and then all in that one pot, you go straight to the carboxylic acid. So that's kind of handy if you know you want to get the carboxylic acid product out. There's no need to reduce and then oxidize in a separate step. We can also use organometallic reagents to create carboxylic acids using either organolithium or Grignard. If we treat those with CO2, with carbon dioxide, we can form a carboxylic acid. Let's take a look at that mechanism. We have either in organolithium or the Grignard, we have an R- equivalent. That's a good nucleophile. And if we take a look at the structure of carbon dioxide, we see a carbonyl here, so that looks like it would be a good electrophile. And so we can have it attack the carbonyl and break the pi bond. And let's take a look at what product that gives us. When we follow those electrons, look what we get. We get a carboxylate salt very close to being the carboxylic acid, right? After step 2, H3O+, we protonate our product, and we get a carboxylic acid out. So that would be a great way of synthesizing a carboxylic acid. This is good for synthesis because we just created a new carbon-carbon bond. We used a carbon nucleophile. We used a carbon electrophile. So this, where the other ones, like the oxidations, which is functional group interconversions, oxidizing carbons that already existed, this is a way of introducing a new carbon and introducing that carbon as a carboxylic acid functional group. Right, this is the new carbon-carbon bond that was formed. So let's see an example where this might come in handy. How about if we started with this alcohol and we wanted to form this carboxylic acid? Now when you compare your starting material to your product, you see we had 1, now we have 2 carbons. So this is a bond that we need to form in this case. So when we do our retrosynthesis, our retrosynthesis says, what starting materials do I need? Well, we recall that this is actually this bond between a carboxylic acid carbonyl and the next carbon over. This is a bond we know how to form. We know how to make because we just saw that. So let's take a look at the 2 carbons involved in this reaction. We want these 2 carbons to come together. One of them must have been a nucleophile. One of them must have been an electrophile. The carbon is now a carboxylic acid, that carbonyl. That was my electrophile. What did he look like before the nucleophile added? This was carbon dioxide. It was a carbonyl and another carbonyl. And what nucleophile, that means this methyl group was my nucleophile somehow. How did I make it a nucleophile? I used a Grignard. So the starting materials I need methyl magnesium bromide, and I need carbon dioxide. If I had these 2 ingredients, I would be able to make this target molecule. So that's a good plan. Let's look back to see where we are. We're at methanol. We need methyl magnesium bromide. So let's think about the Grignard. How do you make a Grignard? You start with the alkyl halide and you throw in some magnesium metal. So what I'll need to do is I'll need to convert this to methyl bromide or methyl iodide if you want. Any halide will do. But we could use PBr3 to convert the alcohol to the bromide. Then we can add in magnesium metal, which will insert itself there and give us the methyl magnesium bromide. And then we're going to take that Grignard and we're going to react with carbon dioxide. But a Grignard reaction is never just throw in the electrophile and you're done. Remember, we need to throw in the electrophile and then we need to work it up. That's where this proton comes from. So this is always going to be a two-step procedure. Step 1 is carbon dioxide. Step 2 is H3O+. We're going to work that up. So very useful to use Grignards and carbon dioxide in synthesis of carboxylic acids. Now, finally, another way that we can form a carboxylic acid is by starting with one of the carboxylic acid derivatives and converting it into a carboxylic acid. Okay, we call this reaction hydrolysis. And if you take any carboxylic acid derivative, remember most of them look like this with the leaving group attached to a carbonyl. But remember the nitrile was in this category too, and this reaction would work as well. If you take these and you react it with water plus some acid catalyst, this also works with base. Okay, but if we do water and acid, we get a hydrolysis, and the product we get is a carboxylic acid. So this is really what defines something as a carboxylic acid derivative, is these are all compounds that upon hydrolysis give a carboxylic acid as a product. Now, you'll either get the carboxylic acid, or if you use base here, what's going to happen in that carboxylic acid? It will get deprotonated. So instead of getting the neutral acid, you would get the carboxylate salt. Okay, but still, clearly, just a proton away from being a carboxylic acid. So what these all have in common, including the nitrile case, is you're taking a functional group that has 3 bonds to heteroatoms, nitrogen, oxygen, halogen, right? With hydrolysis, you convert them to be 3 bonds to oxygen. Okay, so hopefully then even the nitrile, you can see we've gone from 3 CN bonds to 3 CO bonds. That's defined as being a hydrolysis. So let's look at an example of an ester. That's kind of a nice derivative to start with. The ester here has an OR group attached to the carbonyl. Let's see that reaction with sodium hydroxide and water. Now, remember I have a little H3O+ here at the end. We need that because I want to look at the product where I get the neutral carboxylic acid. Now this is another example of an acyl substitution. I hinted that that was going to be the sorts of mechanism we'll see for carboxylic acids and their derivatives. And overall it's going to be a mechanism where we do addition, elimination, addition of our water nucleophile, and elimination of our leaving group. Our leaving group is right here. We're going to be losing methanol in this reaction. Okay, and let's do our mechanism. We have the ester, we have hydroxide. The ester, as usual with our carbonyl, is going to be our electrophile. The hydroxide is going to be our nucleophile. And what's going to happen? Well, the hydroxide is going to attack the carbon, break the pi bond. So as usual, we're going to get a nucleophilic addition to a carbonyl, which gives us an O-. Let's add in our lone pairs. So we add into the carbonyl, and then where does that bring us? Oh, that brings us actually to an intermediate we've seen introduced in this lesson. We have a tetrahedral carbon where at least 2 of the groups, in fact 3 in this case, at least 2 of the groups have a lone pair, and one of them has a charged. We call this a charged tetrahedral intermediate. What happens when you have a charged tetrahedral intermediate? It's going to collapse. So this first step was our addition step. We had addition of our nucleophile into the carbonyl, and our second step here is our elimination step, where we eliminate our leaving group. So what we're going to do here is we're going to do 2 arrows to do this elimination. We call this collapse of a CTI, and it's where the O- reforms the carbonyl and kicks that leaving group out. And our product is going to be our carboxylic acid. Now we just kicked off OCH3 minus. We just lost that group. And we have our carboxylic acid product. Addition, elimination. Okay, however, let me ask, are we done here? Is this our final product? We just formed a carboxylic acid. What kind of reaction conditions do we have? We have base. We have sodium hydroxide. This is not, we're not yet done here because we have a carboxylic acid. Let me redraw this down here. We have an acid in the presence of base. And what I hinted is that every single time you see a carboxylic acid and you're around base, you will have a deprotonation. That is a very favorable reaction. So what's going to happen is we are going to deprotonate, very much favored in the forward direction here, and we'll get the carboxylate. The carboxylate salt is formed. That's our final product in this hydrolysis reaction. Our base catalyzed, and a base promoted. We don't call it catalyzed because in this final step we actually consume our base, an equivalent of our base. We don't get it back anymore because this reaction is so favored in the forward direction. Okay, and then finally, now you can see why we need this step 2 H3O plus is we can protonate our carboxylate and get our carboxylic acid as our final product. And in fact, this deprotonation here drives the equilibrium forward. Because you can see every step that we're doing is reversible. We can have hydroxide add in, and then it can kick back out. Forward and reverse, forward and reverse. Every one of these steps is reversible and they're in equilibrium. But this one last step, when you form the carboxylic acid, this deprotonation is essentially irreversible. So that's what keeps the reaction moving forward, and affecting the overall hydrolysis. Now let's think about this overall substitution reaction that we just did here. Okay, in this case, our nucleophile was hydroxide that we were bringing in, and our leaving group was methoxide. Now, that's kind of interesting because we've never seen an example where an alkoxide was a leaving group. And that's because in the mechanisms we've seen up till now, an alkoxide was not a permissible leaving group. So for example, if we want to do an SN1 or an SN1 or an SN2 or E1 or E2 for that matter, but if we want to do a substitution mechanism that is, unimolecular or bimolecular, something like this, if we thought of this hydroxide coming in and just kicking out methoxide as a leaving group, that would never happen. That's an impossible substitution mechanism. We can only do that substitution if we have an excellent leaving group like chloride, bromide, iodide, a halide, or maybe a tosylate. Okay, so we've never seen that as a leaving group, but it is an okay leaving group for collapse of a CTI. So if we have this mechanism where we have an O- on the same carbon as that methoxide, and we have a tetrahedral carbon, this is our definition of a CTI, a tetrahedral carbon with two groups with lone pairs, then it is possible for that methoxide to kick out because it's not just leaving on its own, it's being pushed out. So we have this push-pull phenomenon going on. And using the two arrows helps you to see that it's not just methoxide dropping off on its own, kind of like an SM1 mechanism might be. It's only dropping off because you have this other group that's capable of pushing it out. That gives us a carbonyl, and that gives us our methoxide leaving group. Okay, the driving force for this reaction, the reason that we can lose methoxide in this case, because methoxide is pretty unstable. That's pretty hard to be on its own. The reason it's okay is because we have formation of a carbonyl. What makes collapse of a CTI great, and that, again, you can see if you use those two arrows, is that pushing out of that leaving group gives a carbonyl, forms a carbonyl in the process. And a carbonyl is a nice, strong, stable, resonance-stabilized functional group. So anytime we can form a carbonyl, that's always going to be a good mechanism. Now this base-promoted ester hydrolysis, that's the reaction we just studied, is called a saponification reaction. It's described as a saponification reaction because it literally can be used to make soap. Now if you think historically, let's just stop for a moment and think about that word. Historically, if you wanted to make soap, or in many parts of the world where people make their own soap, the way you do it is you take animal fat and you treat it with ashes from a fire, and you mix it up with water and you cook it, you boil it. And the solution you get out is a soap solution. Now, a couple questions. How is this working? And also, who in the world thought of this as a good idea to wash clothes? The fact that you're going to take some bacon grease and throw it in some hot water, grab a handful out from the fire, some of the ashes, throw it in there and cook it up. Why would you ever think that would be a good idea to wash your clothes in? This has always kind of fascinated me. And the theory on how this evolved over time was that the women who were washing clothes would maybe have a bucket of water that they would, or a little area of water, a little puddle of water that they were using, and they would maybe use a piece of wood to agitate their clothes as they were washing in the water. And what they noticed was, after a while, after washing your clothes for a while, it would your solution, your washing solution would become more effective. It would be easier to wash clothes at the end of the week than it was at the beginning of the week. And so what was happening was the wood ash was coming from, was the wood that they were using to agitate, and the animal fats were coming from the clothes that we were washing. We're introducing more fats into the solution. So that's when they kind of decided, hey, rather than wait for our soap solution to get good by the end of the week or the end of the month, let's just add this stuff in the beginning and you'd make out a soap solution. Now, as organic chemists, we could take a look at the structures of these components and these molecules to see what's going on. It turns out that animal fats are actually esters, and the wood ash is a source of sodium hydroxide. And so this is the reaction that's taking place. We get a hydrolysis reaction to take place. And what is the product when you take an ester and you treat it with sodium hydroxide in water? Well, you do a hydrolysis and you get the carboxylic acid as usual, but because it's in base, you don't get the carboxylic acid, you get RCO2 minus. Excuse me. You get the carboxylate salt. Now, how does a carboxylate salt act as a soap, and what do the structures of these molecules look like? Let's take a look at that. So the saponification reaction takes a triglyceride. This is a structure of a triglyceride. This you could call a lipid or a fat or an oil. Glycerol is the triol with a 3-carbon with an OH on each carbon. If you mix those with carboxylic acids, these are known as fatty acids because they have really, really long carbon chains on them that make them fatty, make them hydrophobic. And these acids can be either saturated, meaning they have as many hydrogens on them as possible. There's no double bonds, or they could be unsaturated. And of course, you've heard of monounsaturated fats, polyunsaturated fats, saturated fats. These all have to do with the structures of those carbon chains that are part of the triglyceride structure. So we take this triglyceride, these are the animal fats that we're starting with. We treat this with sodium hydroxide and water. What we get is addition, elimination. We get a substitution reaction where hydroxide comes in and kicks out this alcohol on each of these ester groups. So we get back a molecule, this glycerol, that's your leaving group in each case. And then the carboxylate salts, or the carboxylic acid groups that are freed, get deprotonated, and we get these carboxylate salts. Again, this long carbon chains either have double bonds maybe or not. Now, if you take a look at this carboxylate salt, if you have a very, very long carbon chain, we would describe that as being hydrophobic It's a non-polar carbon chain, so that doesn't like water. And here, this carboxylate salt is highly polar. In fact, it's ionic, so you have this hydrophilic part. If you put those into water, what happens is they congregate into something known as a micelle. They're going to arrange themselves in water so into a sphere where the outermost part of the sphere is coated with the hydrophilic heads, the ionic part, and all these hydrophobic tails are buried inside of the sphere to minimize their contact with water. That's called a micelle. This is a very nice model of a micelle. Of course, just a toy, but it works very nice as a model. You can imagine each one of these little rubber strings as being one of those carboxylate salts, carboxylate units. And so the outside is ionic, and it's charged, and so it has a very positive interaction with water. And the inside is all of our hydrophobic, greasy, long carbon chains. Now, how does this work to clean things? Well, if I have my soap solution with all these micelles floating around in it, now if I take my clothing and I agitate it, put it in a washing machine or scrub it on a scrub board or something like that, the grease and oils that are dirty on my clothes are going to make their way onto the inside of this micelle, where it's going to be very nicely dissolved by the interior of the micelle, which is hydrophobic and nonpolar. So the grease works its way inside of this. We describe it as being emulsified when the grease kind of breaks up and gets trapped inside these micelles. And now when I wash my clothes with fresh water, these micelles get washed away and our grease gets washed away at the same time. So that's kind of how soaps work. Now you still could make soap using animal fats, and like I said, around the world they still do that, but we can also have synthetic detergents that have this same general structure. It's not necessarily a sodium carboxylate salt here, because that has some problems making soap scum with hard water and so on. So we can have different kinds of ionic or very polar heads here and various structures for the tails as well, and that's how we end up with a wide variety of soaps and detergents that all have very different cleaning powers. Okay, back to the real world then. That was the base-promoted ester hydrolysis mechanism. Let's take a look at that same reaction, but in acid. We have an ester here, and now we're using H3O+. And in an acid-catalyzed mechanism, we can't have any strong bases around, so there's not going to be any negative charges like we saw in the base-promoted one with hydroxide. So what do you think our first step should be in an acid-promoted reaction, acid-catalyzed reaction? I think I should probably protonate something somewhere because I have acid around, and that's where our carbonyl is going to come into play. I could just use HA to represent H3O+. Our first step is going to be to protonate the carbonyl. Now you could protonate down on this oxygen, and that certainly will happen, but remember, every protonation is reversible, so that's not something that's going to lead to products, so that's not something we're going to concern ourselves with right now. But let's protonate the carbonyl. And by doing so, we take a carbonyl, which is a good electrophile, and we add a positive charge to it. We make it even more electron efficient. This is now a great electrophile, a super electrophile. So I'm going to look around for a nucleophile to add. What nucleophile is there? Of course, there's water. So H3O+ means I have H2O and some strong acid, HA. So sometimes you'll see it drawn this way. Sometimes you might see it drawn this way. But either way, you certainly have water around to be your nucleophile, and that water is going to attack the carbonyl and break the pi bond. It gives me an OH up here, and this oxygen from water still has the two hydrogens on it. And what else? How many lone pairs? It has just one lone pair, because the other lone pair is right here now. It's being shared as this covalent bond. So it has one lone pair left, and that looks like a 1, 2, 3, 4, 5, oxygen 1, 6. Looks like an O+. So I'm going to protonate, and then attack, and then what do I do last? I need to get rid of that positive charge. I'm going to deprotonate. Protonate, attack, deprotonate. This pattern we're going to see again and again and again. So I can use water to come back in, or I could use A- like I had in that first step. Something to deprotonate. And what I've done so far is I have done my addition of my nucleophile. Remember, I want to do a substitution. So I want to add in my nucleophile, and then what do I want to do? I need to eliminate my leaving group. I need to get rid of my leaving group. So who is my leaving group going to be? It's going to be this methoxy group. How do I make it a good leaving group? An acid, how do I make it a good leaving group? I need to protonate it. So I'll bring my HA back in. Protonate the methoxy group to be a good leaving group. Now I have a good leaving group, and what else do I have? How would you describe this intermediate? It looks like I have a CTI, I have a charged tetrahedral intermediate. I have a tetrahedral carbon, 2 or more groups of lone pairs, one of them is charged. I'm in the perfect situation to do collapse of a CTI. Okay, remember 2 arrows to do this collapse. So in other words, don't just lose the leaving group on its own. Have one of these other groups, actually doesn't matter which one you use, have one of these other groups push it out. That's the whole point of being a CTI and doing carbonyl mechanisms, is that you form the carbonyl as our leaving group leaves. Okay. Now what leaving group did I have? My methanol just got kicked out. So that's one of the products of my reaction. Notice we need to have methanol as a leaving group. We can't have methoxide in this case because methoxide is a very strong base and is not compatible with acidic conditions. So remember, no O- or CH3O- in this case in acid. So I need to protonate first. That gives me a nice CTI. That gives me a good leaving group. And now I can collapse. Okay, and now when I do that with my 2 arrows, look how close I am. All I need to do is deprotonate up here, so I can use water to come back in. Or I could use A-. I keep switching back and forth, sorry. So I used HA down here. So now I could use A- to come in and deprotonate. And I'm done. I've done my hydrolysis of an ester to give a carboxylic acid. This is going to be common of acid catalyzed mechanisms are going to be significantly longer than the base catalyzed ones or base promoted ones. So the base ones are good to work on initially, get the hang of it, understand the addition, elimination, and the use of CTIs. Okay, those are all going to have negative charges. In acid, we're going to have positive charges, and the same general idea is going to happen. At some point, we're adding in our nucleophile. At some point, we're losing our leaving group. There's just a lot of other protonations and deprotonations mixed in to avoid our negative charges. So let me just point out, we've seen the acid catalyzed, we've seen the base promoted. I want to point out that one of those is required. Some sort of catalysis is required, either acid or base conditions, in order for this hydrolysis to take place. Okay, we cannot take a neutral ester, which is a weak electrophile, and neutral water, which is a weak nucleophile, and expect the two to come together. If we tried that, let's try it. Just have neutral water attack a neutral ester. Look at what we get. I now have an O- up here, and down here I have an O+. Okay, that's when you know you've made a mistake in a mechanism. Because I can't have a strongly basic O- ever in the same sort of reaction conditions that I would have a strongly acidic O+. So there's no O- and O+ in the same mechanism. That's good to keep in mind, and that's good to help guide you and help you pick up when you maybe have made a mistake. So this is not going to happen. So instead, how does it work? Well, in base, you have in basic conditions, you increase the nucleophilicity of something. So how does this get adjusted in base? You don't have water attacking. You have a strong nucleophile hydroxide attacking. Okay, then you have an O-, it attacks. You have another O-, and so on. Okay, how about an acid? How would I change this in acid to make the mechanism acceptable? Well, in acid, the very first step is protonating the carbonyl. So in acid, we don't have a neutral ester, we have a protonated ester. We have a protonated carbonyl, which is an excellent electrophile. So in base, you find negative charges and strong nucleophiles. In acid, you find positive charges and strong electrophiles. We're going to see this pattern coming in again and again and again. So this is an excellent time for you to get used to that. Now let's just take a look at a nitrile example, because the nitrile looks a little different than the ester. All the other carboxylic acid derivatives would have essentially the same mechanism as the ester, but the nitrile looks a little different, so let's see how we would handle that. Now first of all, when we do a hydrolysis on an amide, there's two possible products you can get. If you do just a mild hydrolysis, we can replace two of the CN bonds with CO bonds and come with and resulting in an amide product. So we would describe this as being partial hydrolysis. And if we wanted to have more vigorous conditions where we have, let's say, H3O plus and heat, we wouldn't stop at the amide. We would continue doing a hydrolysis of the amide. We know the amide is a carboxylic acid derivative as well, right? So it can also undergo hydrolysis. So we have addition, elimination, addition of water, and elimination of the nitrogen-leaving group. And we would ultimately get a carboxylic acid product, okay? But this is kind of handy because this is another way that we can create an amide, we'll see down the line, is by partial hydrolysis of a nitrile. So let's see if we can do this mechanism. This mechanism is just like the ester, very similar to the ester. So we've already seen something on how to do this transformation, but let's see how we can go from a nitrile to an amide. That's a little less intuitive. So we have acetonitrile is this nitrile. We have H3O plus. Our first step, I'm thinking, is going to be to protonate, because we have an acid. Let's write that out. So protonate first. And where do we protonate? Well, the best course of action is to treat the nitrile, the CN triple bond, just like it was a carbonyl. So do exactly what you would expect a carbonyl to do. I'm going to take the lone pair on nitrogen and protonate. Just like I would protonate a carbonyl, I could protonate a nitrile. And just like protonation of the carbonyl made it a great electrophile, protonation of the amide also makes it a great electrophile. So we can look around for a nucleophile. We'll have water here in this hydrolysis reaction as our nucleophile. And how are they going to react? Well, just like they would for a carbonyl. This oxygen is going to attack the carbon and break the pi bond. Totally analogous to a carbonyl. This oxygen still has two hydrogens on it and a lone pair. So it's going to be an O plus. And we now have a double bond between the carbon and the nitrogen instead of a triple bond. Okay, so what do? We protonate, and then we attacked, and now we can deprotonate. Same pattern we've seen again and again for acid catalyzed. So protonate and then attack, and now we can bring water back in as our base and deprotonate. Okay, well this doesn't seem like we're a lot closer, perhaps, but let me show where we are and think about where we're going. The initial product, the first intermediate product that we get in this hydrolysis is going to be the amide. So let me draw the amide so that you can write an upside down amide. Let's see if you can now think a little more clearly and identify what it is we have to do. This is a double bond with an OH here, and we are converting that to a carbonyl. Okay, this structure is kind of like an enol structure, which you may or may not have seen yet in a keto-enol tautomerization. But it's a very similar mechanism. What we need to do is tautomerize. I'll just put this in parentheses because you may not have seen that topic yet for ketones and aldehydes. But either way, when we compare these two structures, what we see is that here we have an NH and now we have an NH2. So one thing we have to do is we have to protonate here. Right? At some point we have to protonate here. And down on the oxygen we have an OH and it ends up being just an oxygen. So another thing we need to do is we need to deprotonate here. And it turns out that those are the exact two steps that we have to do for the remainder of this mechanism. We have to protonate and deprotonate because we are in acidic conditions. Just like up here we protonated first, we're going to do the same thing here. We're going to protonate first, and then we're going to deprotonate second. So how can I protonate this nitrogen? Well, you can think of using the lone pair, but our mechanism is going to be a little cleaner if we use the pi bond. So I can bring in another equivalent of H3O plus and protonate the pi bond. Just like protonating an alkene, you break the pi bond, you add a proton to one atom, and you get a positive charge on the other atom. So I protonate to get a carbocation. That was step 1. Step 2, I need to deprotonate. Let's look at where we are and where we have to go. Do you see how close we are? Let's bring water in as our base. Grab that proton, and instead of having these electrons go and sit on the oxygen to give me an O- and a C+, I'll go straight to the beta resonance form where those two electrons go to be a pi bond, and we're done. We have formed an amide. Okay, so we start out similar to what we would do for a carbonyl, protonate, attack, deprotonate. Okay, but then the second step is a conversion of one structure to another structure, and knowing where you're headed is really the key to getting this mechanism down correctly. Okay, now the conversion of the amide to a carboxylic acid, we'll just say etc. That's going to be the same analogous one as the ester. We're going to do addition of the water and elimination of the nitrogen leaving group in this case. Now it's really cool about having a nitrile and knowing that a nitrile can be converted to either an amide or to a carboxylic acid is we can use this, we can exploit this in synthesis because cyanide is, there's a little lone pair here too, cyanide is a good nucleophile. So there are strategies to get the nitrile functional group into a carbon chain. So let's see an example where that might come in handy. So we have a 3-carbon chain here, and we want to convert it to this new compound. We still see our 3-carbon chain, but we see that there's this new carbon that's added on, and we need to synthesize that. Okay, now let's think about a retrosynthesis. What starting materials do I need? There's actually a few different approaches we can have for this. One of them would be the nitrile that we just saw. So one approach is we just saw that where you now have a carboxylic acid that could have come from a nitrile. In other words, if I had this nitrile, I could do a hydrolysis to get this carboxylic acid product. Okay, so that would be a good strategy. Now we have to do this disconnection and ask ourselves, if we wanted these two carbons to come together and react, how could we do that? One of them must have been a nucleophile. One of them must have been an electrophile. Well, what we're remembering is that cyanide is a good nucleophile, so this certainly was my nucleophile, but that means this carbon was my electrophile. Somehow I have to make that carbon electrophilic. Well, I'm starting with isopropyl chloride. I'm starting with a leaving group in that position. It's already electrophilic. So I think I've done enough planning here to think about my synthesis so I can go ahead and do my transformation. I think my first step is to treat this alkyl halide with sodium cyanide to do an SN2 mechanism. That will replace the leaving group with the cyano group. And once I have the cyano group, now I can convert it to the carboxylic acid by hydrolysis. I want to trade those CN bonds for CO bonds. That's hydrolysis, H3O+. Remember, some heat is required because we want it to not stop at the amide. We want it to go all the way to the carboxylic acid. That's a kind of a forcing reaction. Okay, so nitriles are very handy this way as a way to synthesize carboxylic acids. One last look at this problem. There's another strategy that we can think of. We've actually seen this as another way to make carboxylic acids would be exactly this disconnection as well. What if we asked about these two carbons right away and think about, instead of doing a functional group interconversion right here back to a nitrile, what if we did a disconnection right away and asked about these two carbons? Which one could have been a good nucleophile? Which one was an electrophile? What reaction have we seen that comes together and forms a carboxylic acid? How about if this carbon was my electrophile? What would that electrophile look like? A carbon with two oxygens. We could have carbon dioxide as an electrophile. What nucleophile would react with carbon dioxide to give this target molecule then? How about if I had a Grignard as my nucleophile, then that would react with CO2 and it would give this target molecule exactly. Okay, so that's another approach we can take. Let's see how that would look. Well, we're starting with a chloride. I know with the Grignard we usually think magnesium bromide, but remember a Grignard can be any halide, so we don't have to change that. We could just throw in our magnesium right away and make the magnesium chloride Grignard. Now I have a good nucleophile. What did I want to do with that nucleophile? I wanted to react with carbon dioxide. So remember, that's a two-step process. First, I can add in carbon dioxide. And second, I could do the H3O+ workup to protonate. And so this would give another strategy. So in this lesson, we've been introduced to carboxylic acids, looked at their acidity and their other physical properties. And then we've also seen different ways to synthesize carboxylic acids. We looked at oxidation reactions. We looked at Grignard reactions to form them. And then we looked at carboxylic acid derivative hydrolysis as another way to form carboxylic acids. So we studied the mechanism of that hydrolysis reaction. And in the next lesson, we're going to look again at these carboxylic acid derivatives and think about what reactions do they undergo and how can we synthesize each of those functional groups. So I look forward to seeing you then. Thanks for visiting educator.com.